Okay, we are going to tackle the tricky yet very important algebraic concept of solving simultaneous equations by substitution. This is 8M4 lesson 27. We're going to work a few examples, discuss a few concepts, and I think we're going to make a lot of progress today. I'm very confident. I'm very confident in what we're going to do today. So let's move on over to our screen share, and let's see what we got going on. We have the title. Sorry, this is not, where do we get 7M3? This is not, this is 8M4. This is, we'll just erase that, and we'll just say 8M4, lesson 27, simultaneous equations. Now, what are simultaneous equations? Well, simultaneous equations are typically, it's also known as systems of equations. And that means typically, usually two or more equations, and where, finding where they intersect. Okay, now we've discussed the concept, and so let me give you an example. So let's talk about y equals 3x plus 2 and y equals negative 2x plus 7. Okay, so we have two simultaneous equations. Now, these are both also linear equations. So we have linear, and what we're going to be talking about is, for the most part, equations that are one linear, and we're going to be talking about only two. There are concepts where you talk about more than two linear equations. There's also systems where we talk about a linear equation and a quadratic equation. But in this lesson, we're just talking about two linear equations. And what do we know about linear equations? They can be written, they typically have just a, they have a y and an x, and you can graph them. So let's see what this means to graph these two equations. We know that these linear equations represent lines. So we know that these are both in y equals mx plus b form, and we should know how to graph these. Where the m is the slope, and b is your y-intercept. So we're going to go about graphing these. And if you don't know how to graph these using this format, you could make yourself a t-chart and also graph these by plugging in a value for x and finding out the equivalent value for y and just making a number of points and making a line. But we're going to graph these using this higher form of that we know about, this higher form of graphing, just for purposes of seeing what it means to solve a system of equations. So let's graph this first thing. Y equals 3x plus 2. So we go to our 2, which is our y-intercept. We know that this is a point on the line, 0, 2, because that's our y-intercept, right? This 2 is our y-intercept. And now we're going to find the next point by using our slope, which is 3. Our slope is 3, so that means we can go up 3 and over 1. And we could go up, obviously another 3, and we can go over 1. And this is a legitimate way to plot our points. So let's see. Let's make our line here. Let's use this tool here. Let's just do it like this. Okay. And so we have our line, and we also know that this line goes forever in this direction and forever in this direction. And so any point on this line satisfies this first equation. So let's go and let's graph this second equation, and we'll do the second one in blue. And we know that our y-intercept is 7, so we can find this point 0, 7. And we go down 2 over 1, down 2 over 1, down 2 over 1, and we can make another line here. And so let's make that line like this. Cool. All right, so let's draw our arrow here to represent that this line goes on forever in this direction. Now the question here is, what is our intersection? What is our solution? Our solution, well, if every point on this line makes this first equation true, this is equation 1, and everything on this makes everything on this line makes equation 2 true, then the only point that makes both equations true is this one. This is what we call our solution, because we know this point will make them both true. And this point is what? This point is 1, 5. So our solution to the equation is 1, 5. And that we can see by graphing. This is a graphical solution. But we know that graphing is equivalent to algebra. Descartes taught us that. Anything we can do algebraically, everything we can do graphically, we can do algebraically. Anything we can do algebraically, we can do graphically. That was taught to us by Descartes. He taught us that. And so let's look at this. We're going to look at solving the same system algebraically, and we're going to do it. There's a number of algebraic ways to solve it, but the way we're going to do it right now is by substitution. So let's look at this, and we're going to come back to this 1, 5 solution. It's going to be magic. You're going to see that algebraically, we're going to come up with a 1 and a 5 to answer this equation. So let's look at how we solve this and see if we can make sense of this. Y equals 3x plus 2, and y equals negative 2x plus 7. But first, let me ask you a different question. Let's say that I knew that y equaled 2 and that y is also equal to x. So ignore this thing over here on the left. We're just going to focus our eyes right on this. So if I know that y is 2 and that y is equal to x, so let me go to a different color. So I know that these things are the same. Well, I know that y and y are the same. And I know that y and x are the same. So if I know that 2 is the same as y is obviously the same as y, and y is the same as x, then I also can say that 2 is equal to x. Cool. And how do I know that's true? Well, I know that if y is 2 and y is x, then I can say that this has to be equal to that. Okay, right? So if y is 2 and y is x, then I can say that the two things that y is equal to have to also be the same. So we're going to say 2 is equal to x, right? And we're done. Okay, so let's just ignore that for a sec, or you can stare at that a little longer if you want to, but I'm going to go back over here and ask you a different question. Well, if I know, let me say one more thing about these equations. If I see that y is equal to 3x plus 2, I can't tell you what x is or y is, because if I solve for y, I have this x in it. And if I solve for x, I'd have a y in my answer. So the object when we're dealing with these simultaneous equations is to kind of get rid of one of your variables. But watch what can happen. If I know that y is equal to this, and I know that y is also equal to this, then what can I say about these two things? Well, I know that they have to be equal, because if y is that and y is this, then for them to both be the same thing, they have to be equal. So I'm going to write this like this. 3x plus 2 is equal to negative 2x plus 7. Just like I did over here, if I knew y was 2 and y is x, I knew that x was equal to 2. Similarly, I can say, well, 3x plus 2 is equal to negative 2x plus 7. And that's by substitution. I'm just saying, substituting the two things that y is equal to and setting them equal to each other. Okay. Well, I'm not done yet. I'm not done yet because I don't know what x is, but I can solve this for x because I've gotten rid of all of my y's. So let's solve. I'm going to add 2x to this side and add 2x to this side. This is just that same old solving stuff that we knew how to do a number of units before. So I get 5x plus 2 equals 7. Now I have a two-step problem. Minus 2, and I get 5x equals 5. And if 5x equals 5, then divide by 5, and I get x equals 1. Well, that's cool. I know what x is. But how do I find out what y is? Right? I need to go back and I need to use either one of these equations. Now, the cool thing is I can use equation 1 or 2 to figure out what my y is. So let's use equation 1, and we're going to substitute back in this x equals 1 to this equation and figure out what y is. So we're going to take this 1 and we're going to plug it right in here for x. So I get y is equal to 3 times, not x now, but 1, because I know that x is 1, plus 2. So we get y is equal to 3 plus 2, or y equals 5. So now I have my answer. X is 1 and y is 5. So if I put those together, I get the point 1, 5. X, y is 1, 5. And lo and behold, what do we have? Our graphical answer and our algebraic answer are the same. Does that deserve a happy cat or what? Now, we need to look at this one more time, and we're going to do another problem that's exactly like this one. Now, I want you to absorb what we learned here and think about it, and we'll just spin our happy cat once because, well, I wish it could meow. If I could meow, we would meow right now. This is the whole key to learning how to solve simultaneous equations by substitution. So I'm going to go over here, and I'm just basically going to erase everything that we've done so far. So bear with me. And everything except, how come Happy Cat's still there? I don't know. We're going to get rid of Happy Cat. And we're going to start one more time. And this time we're going to solve another equation, which is y equals 2x plus 4 and y equals negative x minus 2. And we're going to do it graphically and then algebraically. I encourage you to do this on your own. Do this on your own using the same techniques. Okay, now pause and go. Okay, now we're back. Now here we have our m equals 2 and our y int equals 4. Y intercept equals 4. So we go to 4. And we go to, and then our slope is 2. So we go up 2 over 1, up 2 over 1. And then we can make our line. We're just going to make it super long. And then we're going to arrow it off. Now that's this line. Now we're going to make our other line. Our m equals -1, and our y-intercept equals -2. So let's go to -2, where our y-intercept is. We're going to go down 1 over 1, down 1 over 1, and then we're going to make our line. And we're going to just extend it as far as we can through both points. And lo and behold, it looks like this is our intersection point at -2, 0, which is the same thing as x equals -2 and y equals 0. So that's our graphical solution. Now we're going to do our algebraic solution. Now we're going to use algebra. And we have y equals, we're just going to say the same thing, y equals 2x plus 4 and y equals -x minus 2. And again, because we know that y is this and y is also this, that these two must be the same. This is an important concept to understand, that if it's kind of like if a equals b and a equals c, then b equals c. And this is called the this is called the distributive, or sorry, the transitive, basically the transitive property of equality. If one thing equals one thing and one thing equals another, then those two things must be the same. So we know that 2x plus 4 must equal -x minus 2. So we're going to add x to both sides to solve, and then we're going to subtract 4 from both sides. I'm going to do 2 steps in one. So we get 3x equals -6, right? The negative, these cancel and these cancel. So I get 3x is -6. Let's divide by 3 and we get x equals -2. And how do we find y? Well, we have to go back into our either one of our equations, the first or the second one. We'll go to the first one and we'll say y equals 2x plus 4, but x is -2. So we'll say 2 times -2 plus 4. Y equals -4 plus 4, which equals 0. So y equals 0. So our point is x is x comma y. Well, that's -2 comma 0. And lo and behold, our algebraic equation solution and our graphical solution are the same. Again, happy cat. Cool. So you should be familiar and comfortable with doing these two kinds of equations. And then we're going to move along and we're going to look at something that's a little bit different. And we're going to look at an interesting equation. And I want to just draw you the equation first. Well, let's write the equations up here. So if I say y equals 3x plus 2, and I say y equals, y equals 2x plus 1, and y equals 2x plus 3. Now, let's just sit on that for a second. Now let's think about this. Two lines, if I draw any two lines, they will always intersect. If these were straight lines, which they're not, but any two straight lines always intersect. Right? This line and this line, even these two lines they'll intersect somewhere out here, right? They're gonna, if you keep going and you keep going, they will eventually intersect, right? Ones that are like this always intersect if they're almost at right angles, but even ones that are just kind of go side by side will eventually intersect. But there's two kinds of lines that don't have this pattern, and I'm going to show you these because they're really important, and then I'm going to show you how algebraically you can also determine these two types of lines. So let's look at this line here. Y is 2x plus 1. So let's graph that. So here's our 0, 1. This is our y-intercept. It's our y-intercept, and we're going to go up 2 over 1, up 2 over 1, up 2 over 1. And now we're going to create our line. Just a sec, bear with me here. Still learning how to make lines with this thing. So that's our first line. And our second line is y equals 2x plus 3. So let's look at this one. So let's go to our let's make it in a different color. 3. We'll go up 2 over 1, up 2 over 1, up. We can't go really up 2 over 1 there. We'll go, but okay, so let's make this line. So let's continue with drawing this line. Well, look at these lines. This is interesting. These lines, do you think these lines will they ever touch? And the answer is no, because these are a special kind of line. These are parallel lines. And so geometrically, we can see that they will never touch because they're straight, they're parallel, right? Never touch. So most lines that we look at and examine will always intersect. This is an example of one that won't, and we can prove it algebraically because watch what happens. Watch what happens. We're going to use our same strategy of setting these guys equal to each other. So I say 2x plus 1 equals 2x plus 3. We subtract 2x from both sides, and we get this equation that says 1 equals 3. Well, does 1 equal 3? No, never. This is an inconsistent statement. It's invalid. So we get kind of like a not a happy cat. I'm not going to draw a happy cat. We're going to say no, they never intersect. Now we got the right answer, which is they don't intersect, but we have this interesting phenomenon. So if you algebraically come to an inconsistent statement, then the lines don't intersect. Okay, so I'm just showing you this. There's a number of these problems that end up working out like this in chapter 27 in 8M4. So this is how you know that that happens. Now, let me show you a different example that's kind of the same thing, kind of like it, but it's a little bit different. And this is lines that are on top of each other. So how does that happen? Let's look at y equals 2x plus 2 and 2y equals 4x plus 4. Well, this is in graphing format, this first thing. So let's just take that and let's go, well, that's 2, because that's our y-intercept. And then we're going to go up 2 over 1, up 2 over 1, up 2 over 1. And we're going to graph this guy. And let's look at this other line. Well, I can't graph this yet because this is not in graphing format. I have to basically divide everything by 2. And I get y equals 2x plus 2. Well, that's interesting. That's the same graph. I have this 2 up to, and our m is 2. So I go, there's my plus 2. It's my y-intercept. This is my slope. So up 2 over 2. We have the same line. These lines are actually right on top of each other. So they're the same line. Well, they are true everywhere. So it's always, whoops. What am I doing? Always true. So everything on this line is an answer to the problem. And how do we find that that's true? We say, well, if y is 2x plus 2, and then y is also 2x plus 2, well, if we're going to solve it the same way as we did before, we get, well, 2x plus 2 equals 2x plus 2. Subtract 2x, and we get 2 equals 2. Well, that's always true. So our answer is everything on the line is a solution. Okay, so the answer, the key is if you solve a system and you get an equation that is always true, like 2 equals 2, then the entire line is a solution. Okay. Okay, so that's the second key point. So the first key point was how to solve these equations when you end up with one point. This is the kind of point number 2, was sometimes you get parallel lines and you'll get an answer where you get 3 equals 0, and so it's never true. And then sometimes you get something like 2 equals 2 or 1 equals 1, and then it's always true for the line. So any point on this line will make both things true. Okay, that's point number 2. Now point number 3 in this lesson, and this is kind of getting to be a big lesson, but it is all part of the lesson, and so I don't want to leave it out. And that's this. So let's look at how we just solve by substitution. And we're not going to, so now we're going to stop graphing and just solve algebraically by substitution. Okay, so let's look at an equation that we can solve this way. And let's look at this one. So let's look at the system that looks like x plus 9 equals y, and x is equal to 4y minus 6. Well, here I don't have anything. I don't have something of the pattern where I don't have y equals something and y equals something. I just don't have that here. I have a y equals this and an x equals this, but I don't have this pattern. So I need to make this pattern. And we can do it by making my y's the same, but you don't have to just always do it for y. Let's see what can happen. Can I make on this an x be something on both equations? Well, on the second equation, I already have an x equals this. Can we turn this first equation into an equation where we have x equals something? And the answer is yes. So let's look at that. We have x plus 9 equals y. And I want this to be in the form, put in form of x equals something. So the way we do that is we move everything to the other side. So let's subtract 9 from both sides, and we get x, these cancel, equals y minus 9. Now let's look at these equations. Look at the ones I'm circling here. I have x equals this, and I have x equals this. So I can say that if x is this and x is that, then this equals that. So let's say this in algebraic form. 4y minus 6 equals y minus 9. And now I can solve for y. So we're going to subtract y from both sides. And my y's are going to end up over here, so I'm going to add 6 to both sides over here. These cancel, and these cancel. So I get 4y minus y is 3y equals, and negative 9 plus 6 is negative 3. Now we're going to divide both sides by 3, and I get y equals negative 1. Am I done? No, I need to find, now I need to find x. Well, I can look at either equation. Let's look at the easy one here, the one where x equals y minus 9. So I know that y is negative 1, so let's rewrite this guy and say, well, x is equal to y, which is negative 1, minus 9. So negative 1 minus 9 is negative 10. Well, x equals negative 10. So if I put these together, I get x comma y equals negative 10 comma negative 1. And that's my answer. I'm going to box it. And we can check it out using the other equation if we wanted to check it and put a negative 10 and a negative 1 in here. And let's just see if it still works. So we go x, which is negative 10, does that equal 4 times y, which is negative 1 minus 6? Negative 10 equals negative 4 minus 6. Yes, negative 10 equals negative 10. It works. And that is a happy cat. Whew! All right. One last problem. One last problem, and this is the tricky one, and this is the whole ball of wax. Let's just go all the way down here to new document. Happy cat, we'll see you in a second. Okay, so let's try this one. And this one's going to have a fraction in it. Don't let this throw you. Y is equal to 3 halves x minus 6, and 2y is equal to 7 minus 4x. Now, in this case, I don't have, my x's are way off, so I'm not going to try and make those the same. But how could I make these the same? You don't always have to have a y equals something and a y equals something. You could have 2y equals something and 2y equals something. Because in this case, if 2y is this and 2y is that, then these two still are equal because this equals that, and these two things are the same. So I can then say these things are the same. So let's look at this one. I can do that same trick. And let's multiply both sides. What are you going to multiply everything by? Well, if I rewrite this first one by multiplying everything by 2 on the left and on the right, I can get that same thing happening. So let's do that. So we get 2y, and this is distribution. 2 times 3 halves x is 2 times 3 halves is 2, to cancel those 2's. So I get 3x, and multiply my 2 by my negative 6, and I get negative 12. Now I have two things. These two things are equal, so these two things must be equal. So let's write that out. 7 minus 4x equals 3x minus 12. Well, I'm going to add 4x to both sides. And I'm going to get 7 equals, these cancel, equals 7x minus 12. Now I'm going to add 12 to both sides. And I get 7x equals 19. I'm just going to really quickly go and check and make sure that I got the right problem here, because I want to make sure, because this is heading towards a fraction answer, which is fine, but I'm just going to go quickly make sure that I have, if I copied the right problem over. So I have y is 3 half x minus 6 and 2y equals 7 minus 4x. Yep, I sure did. So let's see. So we got 2y equals 3x minus 12. We had 7 minus 4x equals 3x minus 12. We had 4x, we had 7 equals 7x minus 12. Yep, okay, it's looking good. So we've done everything right. And so I get here, we're going to divide both sides by 7. And I get x equals 19 over 7. Kind of ugly fraction. Now let's go back and let's look at this equation, and we're going to use it to find what our y has to be. So we know that 2y equals 3x minus 12. And what we know that x is 19/7. So 2y equals 3 times 19/7 minus 12. I'm going to just put that whole thing up here. We're going to copy it back up here because it's going to take a little bit to solve. So 2y equals 3 times 19 is 57 sevenths minus 12. And I'm just going to convert that right now into (84/7), right? 12 is equal to 84/7. So 2y equals, so 57 minus 84/7. Uh-oh, this is this ugly math, but we're going to do it all, work it all out. 7, 1, 7, 27. So 2y is 27/7. So I got to multiply both sides by a half. And I get y equals 27/14. So our answer is 19/7, 27/14. Wow, if that turns out to be, if it turns out that I did some bad math here, I'll come back and I'll correct it for you later. Otherwise, I'm going to say, dang, that was a hard one. And I'm going to go happy cat on this. And at least the principles are right. And we're going to head back over and sign off and say, this was a lot. We learned a lot today. Cool. And we learned a lot today. So yeah, some of that last stuff got a little bit more involved, but this is the essence of how you solve systems of equations by substitution. And we also even considered the systems of equations where the lines are parallel and never meet, or the ones where they're right on top of each other and we have infinite solutions. But most of the time we have lines that cross in space, and you can solve those by substitution.